Hello friends, today's topic is correlation. Studying this chapter, we should enable to understand the meaning of term correlation, understand the nature of relationship between two variables, calculate the different measures of correlation, and analysis the degree and direction of relationship. Firstly, introduction. Uh, in previous chapters, we learned how to construct summary measures out of the mass of data and changes among the similar variables. Now we will learn how to examine the relationship between two variables. As the summer heat rises, hill stations are crowded with more and more visitors. Ice cream sellers become more brisk. Thus, the temperature is related to number of visitors and sale of ice cream. Similarly, as the supply of tomato increases in your local mandi, its prices drops. When the local harvest starts reaching the market, the price of tomatoes drop from princely rupees 40 per kg to rupees 4 per kg or even less. Thus, supply is related to price. Correlation analysis is a means for examining such relationships systematically. It deals with the questions such as: is there any relationship between two variables? If the value of one variable changes, does the value of other variables changes? Do both variables move in the same direction? How strong is the relationship? Now, the second thing is types of relationship. Let us look at various types of relationship. The relationship between movements in quantity demanded and the price of a commodity is an integral part of the theory of demand, which you will lead in previous classes. Low rainfalls is related to low agriculture productivity. Such examples of relationship may be given a cause and effect relationship interpretation. Other may be just coincidence. The relationship between arrival of migratory birds in a century and the birth rate in the locality can be given any cause and effect interpretation. These relationships are simple coincidence. The relationship between size of the shoes and money your pocket is another such example. Even if a relationship exists, if they are difficult to explain it. In another instance, a third variable impact or two variables may give rise to a relation between the two variables. Brisk sale of ice cream may be related to high number of deaths due to drowning. The victims are not drowned due to the eating of ice creams. Rising temperature leads to brisk sale of ice creams. Moreover, large number of people start going to swimming pools to beat the heat. This might have raised the number of deaths by drowning. Thus, temperature is behind the high correlation between the sale of ice creams and death due to the drowning. What does correlation measures? Correlation studies and measures the direction and intensity of relationship among variables. Correlation measures covariance, covariation, not quotient. Correlation should never be interpreted as implying cause and effect relationship. The presence of correlation between two variables x and y simply means that when the value of one variable is found to change in one direction, the value of other variables is found to change either in the same direction. It may be positive change, or in the opposite direction it may be negative change, but in a definite way. For simplicity, we assume here that the correlation, if it exists, is linear. It is the relative movement of the two variables can be represented by drawing a straight line on a graph paper. Now we learn about types of correlation. Correlation is commonly classified into negative and positive correlation. The correlation is said to be positive when the variables move together in the same direction. When the income rises, consumption also rises. When income falls, consumption also falls. Sale of ice cream and temperature move in the same direction. The correlation is negative when they move in opposite direction. When the price of apple falls, its demand increases. When the prices rises, its demand decreases. When you spend more time in studying, chances of your failing decline. When you spend less hours in study, chances of your failing increases. These are instances of negative correlation. The variables move in opposite direction. Now learn about techniques for measuring correlation. Widely used techniques for a study of correlation are scatter diagrams, Carl-Pearson's coefficient of correlation, and Spearman's rank correlation. A scatter diagram visually represents the nature of association without giving any specific numerical value. A numerical measure of linear relationship between two variables is given by Karl Pearson's coefficient of correlation. A relationship is said to be linear if it can be represented by a straight line. Another measure is Spearman's coefficient of correlation, which measures the linear association between ranks assigned to individual items according to their attributes. Attributes are those variables variables which cannot be numerically measured, such as intelligence of people, physical appearance, honesty, etc. Now, firstly, we learn about scatter diagram. A scatter diagram is a usually technique for visually examine the forms of relationship without calculating any numerical value. In this technique, the value of two variables are plotted up as points on a graph paper. The cluster of points so plotted is referred to as a scatter diagram. From a scatter diagram, one can get a fairly good idea of the nature of relationship. In a scatter diagram, the degree of closeness of scatter points and their overall direction enable us to examine the relationship. If all the points lie on a line, the correlation is perfect and is said to be unity. If the scatter points are widely dispersed around the line, the correlation is low. The correlation is said to be linear if the scatter points lie near a line or on a line. Scatter diagram spanning over figure 7.1 to figure 7.5 give us an idea of the relationship between two variables. Let us see the positive direction, figure 7.1, positive correlation, figure 7.2, negative correlation, figure 7.3, no direction, no correlation, figure 7.4, perfect positive correlation, figure 7.5, perfect negative correlation. If figure 7.1 shows a scatter around an upward rising and line indicating the movement of the variables in the same direction. When x rises, y will also rise. This is positive correlation. In figure 7.2, the points are found to be scattered around a downward sloping line. This time of variables move in opposite directions. When x rises, y falls, and vice versa. This is negative correlation. In figure 7.3, there is no upward rising or downward sloping line around which the points are scattered. This is an example of no correlation. In figure 7.4 and figure 7.5, the points are no longer scattered around an upward rising or downward falling line. The points themselves are on the lines. This is referred to as perfect positive correlation and perfect negative correlation, respectively. Inspection of the scatter diagram gives an idea of the nature and intensity of relationship. Now learn about Karl Pearson's coefficient of correlation. This is also known as product moment correlation and simple correlation coefficient. It gives a precise numerical value of the degree of linear relationship between two variables x and y. The linear relationship may be given as y is equal to a plus bx. This type of relation may be described by a straight line. The interpretation that the line makes on the y-axis is given by a, and the slope of the line is given by b. It gives the change in the value of y for very small change in the value of x. On the other hand, if the relationship cannot be represented by a straight line, as in y is equal to x square, the value of correlation will be 0. It clearly shows that zero correlation need not mean absence of any type of relationship between the two variables. Let us see x1, x2 and so on up to xn be n variables of x, and y1, y2 up to yn be the corresponding values of y. In the subsequent presentation, the subscripts indicating the units are dropped for the sake of simplicity. The arithmetic mean of y and x are defined as x bar is equal to summation x divided by n, and y bar equal to summation y divided by n, and their variance are as follows: sigma square x equal to x minus x bar का whole square summation divided by n, or is equal to summation x square divided by n minus summation x bar square. Similarly, sigma square y, The standard deviations of x and y respectively are the positive square roots of their variance. Covariance of x and y are defined as covariance of x and y is equal to summation x minus x bar multiplied by summation y minus y bar divided by n, or equal to summation small x multiplied by small y divided by n. Small x represent as x minus x bar and small y represents as y x minus y minus y bar are divisions of ith value of x and y from the mean values respectively. The sign of covariance between x and y determines the sign of the correlation coefficient. The standard deviations are always positive if the covariance is 0. The correlation coefficient is always 0. The product moment correlation or the Karl Pearson's measures of correlation is given by R is equal to summation xy divided by n into standard deviation of x and standard deviation of y. Here represent the some formulas. Now discuss about properties of correlation coefficient. Let us now discuss the properties of correlation coefficient. Number 1, R has no unit. It is a pure number. It means units of measurement are not part of R, are between height in feet or weight in kilograms. For instance, is 0.7. A negative value of R indicates an inverse relationship. A change in any in one variable is associated with change in the other variables is the opposite direction. When price of commodity rises, its demands falls. When the rate of interest rises, the demand of funds also falls. It is because now funds have become costlier. If R is positive, the two variables move in the same direction. When the price of coffee, a substitute of tea, rises, the demand for tea also rises. Improvement in irrigation facilities is associated with high yield. When temperature rises, the sale of ice cream becomes brisk. If R is equal to 0, the two variables are uncorrelated. There is no linear relationship between them. However, other types of relation may be there. If R is equal to 1 or R is equal to -1, the correlation is perfect. The relation between them is exact. A high value of R indicates strong linear relationship. Its value is said to be high when it closes to +1 or -1. A low value of R indicates a weak linear relationship. Its value is said to be low when it's close to 0. The value of correlation coefficient lies is between -1 and +1. If in any exercise the value of R is outside this range, it indicates error in correlation. It is important. The value of R is unaffected by the change of origin and change of scale. Give two variables x and y. Let us define two new variables. Use this property is used to calculate correlation coefficient in highly simplified manner as in the steps deviation method. Some examples is there. It shows the correlation between the data. Now we discuss some about Spearman's rank correlation. Spearman's rank correlation was developed by British psychologist C.E. Spearman. It is used when the variables cannot be measured meaningfully, as in the case of price, income, weight, etc. Ranking may be more meaningful when the measurement of the variables are suspect. Consider this situation where we are required to calculate the correlation between height and weight of students in a remote village. Neither measuring roads nor weighting scales are available. The students can be easily ranked in terms of height and weight without using measuring rods and weighting scales. There are also situations when you are required to quantify qualities such as fairness, honesty, etc. Ranking may be better alternative to quantification of qualities. Moreover, sometimes the correlation coefficient between two variables with extreme values may be quite different from the coefficient without the extreme values. Under these circumstances, rank correlation provide a better alternative to simple correlation. Rank correlation coefficient and simple correlation coefficient have the same interpretation. Its formula has been derived from simple correlation coefficient where individual values have been replaced by ranks. These ranks are used for calculation of correlation. This coefficient provide a measure of linear association between rank assigned to these units. Note their values. It is product movement correlation between the ranks. Its formula is RK, yani rank correlation, equal to 1 minus 6 sigma d square divided by n square n minus n. Some examples calculating rank correlation. Now the conclusion. The scattered diagram gives a visual representation of the relationship between and is not confined to linear relations. Measures of correlation such as Karl Pearson coefficient of correlation and Spearman's rank correlations are strictly the measure of linear relationship. When the variables cannot be measured precisely, rank correlation can meaningfully be used. These measures, however, do not imply caution. The knowledge of correlation gives as an idea of the direction and intensity of change in a variables when the correlation variables changes.